Imagine a universe where every particle you know has a hidden partner. Supersymmetry, or SUSY for short, proposes a symmetry between particles with integer spin, called bosons, and particles with half-integer spin, known as fermions. In simple terms, it suggests that for every known particle there exists a superpartner with different spin properties. Why is this important? Well, if we discover evidence for supersymmetry, it could solve some of the biggest puzzles in physics. In a supersymmetric theory, the equations governing force and matter are identical. This means that bosons and fermions could transform into each other under certain conditions. For example, if the electron has a supersymmetric partner, it would be called a selectron, a scalar particle with different spin properties. So, why haven't we seen these superpartners yet? Despite extensive experiments, like those at the Large Hadron Collider, no direct evidence of supersymmetric particles has been found. This doesn't mean they don't exist. They might just be hiding at energy levels beyond our current reach. It has applications in various fields like quantum mechanics, condensed matter physics, and even astrophysics. For instance, in high-energy physics, a supersymmetric extension of the Standard Model could offer a framework for understanding physics beyond our current theories. Exciting stuff, right? But hold on, supersymmetry isn't without its skeptics. Some argue that the lack of experimental evidence is a significant red flag. Others believe it's only a matter of time before we unlock its secrets. So, what's next for supersymmetry? One reason that physicists explored supersymmetry is because it offers an extension to the more familiar symmetries of quantum field theory. These symmetries are grouped into the Poincaré group and internal symmetries. The Coleman-Mandula theorem showed that, under certain assumptions, the symmetries of the S matrix must be a direct product of the Poincaré group with a compact internal symmetry group, or if there is no mass gap, the conformal group with a compact internal symmetry group. In 1971, physicists Golfand and Leichtman were the first to show that the Poincaré algebra could be extended through the introduction of 4 anti-commuting spinor generators in 4 dimensions. These generators later became known as supercharges. Then in 1975, the Haag-Lopusanski-Sohnius theorem analyzed all possible superalgebras in general form, including those with an extended number of supergenerators and central charges. This extended super-Poincaré algebra paved the way for obtaining a very large and important class of supersymmetric field theories. Traditional symmetries of physics are generated by objects that transform by the tensor representations of the Poincaré group and internal symmetries. Supersymmetries, however, are generated by objects that transform by the spin representations. According to the spin statistics theorem, bosonic fields commute while fermionic fields anticommute. Combining these two kinds of fields into a single algebra requires the introduction of a Z2 grading under which the bosons are the even elements and the fermions are the odd elements. Such an algebra is called a Lie superalgebra. Supersymmetric quantum mechanics adds the SUSY superalgebra to quantum mechanics as opposed to quantum field theory. Supersymmetric quantum mechanics often becomes relevant when studying the dynamics of supersymmetric solitons. And due to the simplified nature of having fields which are only functions of time rather than spacetime, significant progress has been made in this subject. It is now studied in its own right. SUSY quantum mechanics involves pairs of Hamiltonians which share a particular mathematical relationship, known as partner Hamiltonians. The potential energy terms which occur in the Hamiltonians are then known as partner potentials. An introductory theorem shows that for every eigenstate of one Hamiltonian, its partner Hamiltonian has a corresponding eigenstate with the same energy. This fact can be exploited to deduce many properties of the eigenstate spectrum. It is analogous to the original description of SUSY, which referred to bosons and fermions. In quantum field theory, supersymmetry is motivated by solutions to several theoretical problems. It generally provides many desirable mathematical properties and ensures sensible behavior at high energies. Supersymmetric quantum field theory is often much easier to analyze, as many more problems become mathematically tractable. When supersymmetry is imposed as a local symmetry, Einstein's theory of general relativity is included automatically. The result is said to be a theory of supergravity. Another theoretically appealing property of supersymmetry is that it offers the only loophole to the Coleman-Mandula theorem, which prohibits spacetime and internal symmetries from being combined in any non-trivial way for quantum field theories with very general assumptions. The Haag-Lopusansky-Sonius theorem demonstrates that supersymmetry is the only way spacetime and internal symmetries can be combined consistently. While supersymmetry has not been discovered at high energy, it was found to be effectively realized at the intermediate energy of hadronic physics, where baryons and mesons are superpartners. An exception is the pion, which appears as a zero mode in the mass spectrum and thus protected by supersymmetry. It has no baryonic partner. The realization of this effective supersymmetry is readily explained in quark-d-quark models, because two different color charges close together, like blue and red, appear under coarse resolution as the corresponding anticolor, like anti-green. A d-quark cluster viewed with coarse resolution effectively appears as an antiquark. Therefore, a baryon containing three valence quarks, of which two tend to cluster together as a d-quark, behaves like a meson. All stochastic differential equations, the models for all types of continuous time dynamical systems, possess topological supersymmetry. In the operator representation of stochastic evolution, the topological supersymmetry is the exterior derivative, which is commutative, with the stochastic evolution operator defined as the stochastically averaged pullback, induced on differential forms by SDE-defined diffeomorphisms of the phase space. The topological sector of the emerging supersymmetric theory of stochastic dynamics can be recognized as the Witten-type topological field theory. The meaning of the topological supersymmetry in dynamical systems is the preservation of the phase space continuity. Infinitely close points will remain close during continuous time evolution, even in the presence of noise. When the topological supersymmetry is broken spontaneously, this property is violated in the limit of infinitely long temporal evolution. The model can be said to exhibit the stochastic generalization of the butterfly effect. From a more general perspective, spontaneous breakdown of the topological supersymmetry is the theoretical essence of the ubiquitous dynamical phenomenon variously known as chaos, turbulence, self-organized criticality, and more. The Goldstone theorem explains the associated emergence of the long-range dynamical behavior that manifests itself as 1 per f noise, butterfly effect, and the scale-free statistics of sudden processes such as earthquakes, neuroavalanches, and solar flares, known as Zipf's law and the Richter scale.